Hey guys, welcome. This is the promised second of 3 videos investigating the nth roots of complex numbers. Right? Now, in the first video, we accomplished a lot. In particular, we answered the question, what are the 3 cube roots of 8i? And using that as a starting point, we also came up with a general formula for the nth root of any complex number z. Yeah, so that's a lot to accomplish in that first video. And you ought to check out that first video before you keep watching this. But natural then that in this video we try to answer this question. And this question should technically say, what are the 3 cube roots of 1? Unity just means 1. So the question we're trying to answer is this, but actually should say, what are the 3 cube roots of 1? Because, as I said in the first video, every complex number has 3 cube roots. And so, since 1, which is a real number, is therefore a complex number, 1 should also have 3 cube roots. Now, obviously, 1 is one of the 3 cube roots of 1. But what are the other 2 is kind of the mystery. Well, we're going to answer this question in 3 different ways. First, let's do algebra that should be all too familiar to you at this point. Now, notice that saying the complex number z is the cube root of 1 is the same thing as saying that z cubed is equal to 1, right? Okay, but then this is the same thing as saying z cubed minus 1 is equal to 0. This here is the same thing as this here. But then we realize that 1 is a perfect cube, so we can write instead of this. Cool. And then we recall in algebra that a cubed minus b cubed, which is called difference of cubes, has a special formula, namely this. And so in our situation here, z is a and 1 is b. So then using the right hand side, we see that we can write z cubed minus 1 cubed, which is the same as this, and in turn the same as this, and in turn same as trying to answer this as soon as we find z, right? Like this here is the same as this here. But then from this, we set this equal to 0 and find our obvious z equals 1. And then we set this equal to 0, and this is a quadratic, and we can solve it using the quadratic formula if all else fails. And in fact, we can complete the square on this quadratic and solve it that way, but quadratic formula, why not? So you plug the quadratic formula, plug into the quadratic formula, if I'm careful with my words, and you'd find that the 2 z's that we're missing are these 2. And if you simplify it a little bit, it's a bit more revealing what they look like. That is this, and actually, we can say this, right? Like, we can split these 2 into their 2 parts, minus 1 plus I root 3 over 2, and minus 1 minus I root 3 over 2, and then in turn split that into 2 fractions each. And so yeah, now this guy was the obvious one, and then these 2. Like, if you cube this here or this here, these 2 complex numbers, and this 2, remember, is a complex number. It's just 1 plus 0i. But yeah, anyway, if you cube these 2, you're going to find that you're going to get 1. So these are the 3 cube roots of 1. But wait, this is not what we did in the first video. We didn't do this. This is just convenient because, well, difference of cubes would allow you to find the other 2. Like, there isn't an equivalent, difference of 4th powers that would allow you to find all 4 4th roots of 1 if you started off with z to the 4 is equal to 1 and proceeded in this manner, right? So it's lucky that difference of cubes always allows you to find all 3 answers if you set this equal to 0, which is set this equal to 0, and you get it. So it's just like a convenient algebra trick that happens to be in our toolbox, and we can just reach out to it. This doesn't always work, but the formula that we came up with in the first video does always work. But before we use the formula, there's a second option that I talked about briefly in that first video, which is this. There is a really nice geometry about nth roots of complex numbers, right? In general, for the nth root of any complex number, the nth roots are going to be spread apart 360 divided by n degrees, right? So if you can find one of them, you could just add 360 divided by n degrees to that one to find another one. So this is what I'm saying. Since here n is 3, since we're talking about cube roots, the cube roots of any complex number, and therefore the cube roots of any number that we talk about, because really, like, we talk about complex and real numbers and nothing else that I know of. So for any number that we want, its cube roots are going to be spread 120 degrees apart, because, as I said, 360 divided by n here is 3 would be 120. And so once you find one of them, in this case we already could easily see that one of the cube roots of 1 is 1, and that would be like right here, and so that'd be at 1 comma 0 degrees. And since it's a cube root, we're trying to find other cube roots. We know that the cube roots are going to be spread 120 degrees apart, so we can add 120 degrees to this to get to this one, and then 120 degrees to get to this one. Now, yes, these are not complex numbers. These are just placeholders for the r and the theta and r cis theta, which are completely deterministic of the complex number, right? All you need to determine a complex number in polar form is its r and its theta. And so that's why, in my visual, it's sufficient for the 3 cube roots to specify their r and their theta. Yeah? Okay. But basically, this is another option I'm saying, is instead of doing the algebra we showed to start, you could do this, which is, you can start with 1. No cube roots are going to be spread 120 degrees apart. Fourth roots are going to be spread 90 degrees apart. So as soon as you find one of the roots, you could just add 360 divided by n to get to the others. And so you could take this approach. And as I said, in r cis theta form, right? Like, if we have the r and the theta, we can completely determine what complex number it is, and we can convert it into rectangular form, which is what these guys are called if we so choose. So, for example, we can check that this is, in fact, this guy, because, well, it would be 1 cis 120, right? And because, well, that's the r and that's the theta, and it's an r cis theta form. And so 1 cis 120 is going to be, well, 1 times cosine 120 plus I times sine 120, and so we distribute the 1 that to cosine 120 plus I times sine 120. That's what this abbreviation says. And so once we distribute the 1, it's going to look like this, and you figure out what cosine 120 is and what sine 120 is, and if you do, then you're going to find that this here is that complex number. And yes, as I said in the first video, when you're visually representing complex numbers, you don't have the circle or these lines. I'm just trying to help you out. But otherwise, the complex numbers in the real and imaginary axis are just points, right? Yeah, so we have a point there, that's 1, and then a point there for this complex number. No, sorry, not there, rather right there for this complex number, right there, right? And then a point there for this complex number, and this complex number, which is where we're going next, is 1 cis 240, which is that, which in turn is this, and so there we are. And so, yeah, like if we went with the visual, we could still write them in this form. It's just we need to first plug in the r and the theta and r cis theta, and then use this longer format and then calculate these guys. Yeah? Okay, cool. And the final way that we're going to do the 3 cube roots of 1, of course, is using the formula. And the general formula that we came up with in the first video, right, was this here, right? And so since we're doing cube roots here, n is 3, and so k would go 0, 1, and then 3 minus 1 is 2, so just 0, 1, 2. That's what k would range over. And then n here is 3, and theta for 1, as you saw it in the visual, is going to be 0 degrees, because 1 is at 0 degrees, right? Like, just a quick reminder. But yeah, like, so we have it all. So first we replace the n with 3, because we're looking for cube roots, and that of course means that this tail end would have to look like this. And then so this is your second practice on using this formula, so it shouldn't be so bad. And so then, next I show that the theta is 0, and this is again because the complex number we're taking the cube root of, which is 1, is at 1 comma 0 as far as r comma theta format. Okay, and so then next we go, let's replace the k beginning with 0 and then 1 and then 2, and that's going to give us the 3 cube roots, right? Because everything else is plugged in. Theta is plugged in, n is plugged in, so all that is left to do is to plug in the k beginning with 0 and then 1 and then 2. And notice I've done some simplifying here since we know n is 3. 360 over 3 is 120, so this is 120 times k. So first 120 times 0 in that part, and so this part is 0 also, and so we get the z, the first root is going to be and this is 1, so it's going to be cis 0 plus 0, and that's just cis 0, that's cosine 0 plus I times sine 0. Cosine 0 is 1, sine 0 is 0, and so we get 1. Alright, well, this is a fancy way of writing 1, all this, but okay, so we knew all along that this was the first root, so the formula doesn't lie. And then when k is equal to 1, we get this here, and you've been through the ropes now, so there we are, and that's that guy, and finalement this guy, right? And we are done. Yeah, cool. Alright, I hope you enjoyed this, and one more video on the nth roots of complex numbers.